All right, physics, welcome to another flip lecture. Here we go. We're going to be diving into chapter 12 today. Chapter 12 is review for you. You have had this before in physical science. We're going to be talking about periodic motion. And this does go into a little bit more detail than the physical science portion, but all of the main concepts you have had before. This is a week of remembering, not a week of learning, I hope. So we're going to draw on some prior knowledge here for you. We're going to be diving into periodic motion, which can be described as simple harmonic motion. Any motion which repeats at a constant rate is called periodic motion. So this is periodic motion. I'm doing the same thing at approximately the same rate of time. Okay? This is pretty exciting. I know you could watch this all day, right? Periodic motion is any motion that repeats at a constant rate. If this motion is self-sustaining, obviously not my hands clapping, that was me and my muscles doing that, but if this motion is self-sustaining, without friction, it will continue forever. Now we know that in the real world, there is friction, and so in the real world, periodic motion comes to a stop. But in the idealized sense of high school physics, it goes on forever. It's pretty cool. So this kind of motion without unbalanced friction forces will continue forever. It is driven by a restoring force, and that restoring force is what is there to bring the system back to a position of rest, which we call equilibrium. And I'll show you a picture that will clarify all these terms here in just a moment. The restoring force is dependent on displacement, how far away from the equilibrium point you have moved the system, you've disturbed the system before it starts moving, and the restoring constant, or basically how much the system wants to return to equilibrium. So let me show you a picture that will help all of these terms come to light. So here I have periodic motion in an oscillating spring, okay? And this spring, it has a mass on the bottom of it, and it is bouncing up and down. It is oscillating with periodic motion, and you can see that this motion will go on forever without the presence of friction. And because it's an animated GIF, yes, it will go on forever because there's no friction in my animation. But in a real world setting, there's air resistance and the resistance within the moving molecules of the spring that would eventually slow it down and stop it, but not for a long, long, long time. Okay, so a mass on a spring with a spring constant of 4.9 newtons per meter oscillates 0.2 meters from the equilibrium position in either direction. What is the restoring force at the bottom of the oscillation? So the equilibrium point I've indicated is this red line. If the spring could have a perfect world, the mass would just be sitting there, centered on that red line, but somebody has disturbed the system. They've pulled it down and let it go. So it is bouncing up and down. At the bottom, what is the restoring force pulling it upward? Okay, so what is the restoring force right now? Okay, well, the restoring force at that point is negative k times x. Why negative? Well, because the displacement is going to be in a vector away from equilibrium, and the restoring force is going to be in a vector towards equilibrium. So it's the opposite direction. The magnitude is the same, but the sign is different. The arrow is pointing the other direction. So force, the restoring force is negative. I'm just going to represent that as -1 because I'm going to show you something cool in just a moment. Times the restoring force, or the constant, 4.9 newtons per meter, times the displacement, which is -0.2 meters. So again, -0.2 meters because we're down from the point of equilibrium by 0.2 meters. Okay. So I'm just going to rearrange this using the commutative property of multiplication. -1 times -0.2. Oh, look, that's just 0.2. Okay, now we're a little bit happier. So 0.2 times 4.9 is 0.98. I only have one significant digit here, so I've got to round this to 1. So the restoring force is 1 Newton with a constant, a spring constant of 4.9 and a displacement of -0.2 meters. Okay, so that's the way you calculate restoring force. Restoring force is always going to be pointing towards the equilibrium point. So if I had done it above, then my x would have been positive and my restoring force would have been pointing in the negative direction because it's always pointing opposite the vector of displacement. Okay, here we go. Moving on. Harmonic motion, some terminology you need. We need to know the word amplitude, which is the maximum displacement from equilibrium. Okay, and we need to know the term period, which is not the little point at the end of a sentence. Period in this sense is how long it takes to go from some point in the cycle back to that same point in the cycle. What's the time per cycle? Okay, and frequency is the opposite of that. Frequency is not the time per cycle, but it's the cycles per unit time. In this case, it's cycles per second, and we use the unit hertz to reference that. So let me show you a picture. Okay, here I have another spring oscillating with a mass at the end of it, and a neat little animation that helps you see it as a waveform. Okay, so this is time going this way, and we start at negative A amplitude, and then it goes up to positive A amplitude, and then back to negative A amplitude. So the amplitude is the distance from equilibrium point to maximum displacement. And the absolute value of amplitude is always the same whether you're on one side of the oscillation or the other. Positive A or negative A, it's just the direction that it's oscillating. Okay, so amplitude is the distance from equilibrium to maximum displacement. Okay, it can be positive or negative. And in this particular example, this period is approximately 5 seconds. 1, 2, 3, 4, 5-ish seconds, right? So the period here, we're going to say, is about 5 seconds. It takes to get from negative A back to negative A. Negative A back to negative A. Okay, that's about 5 seconds. So the frequency would then be 1 over 5 because the frequency is just the inverse of the period. So that would be 0.2 hertz, 1 divided by 5. Okay, so frequency and period are inverses. Amplitude is the maximum displacement from equilibrium. So if you need to calculate period, you want to know how far is it in time between two corresponding parts of the adjacent cycles. There's a formula you can use here. And so it is, the period is twice pi times the square root of the mass of the oscillating object divided by the restoring force constant, or the spring constant, if it's a spring. So really this part doesn't change. It's just this part that changes, the mass and the spring constant. That's really all you need to know. So if you have those, you can calculate the oscillation. Notice that the magnitude of displacement is irrelevant. Amplitude is not anywhere in there. So if I have that oscillating spring system and I pull the spring down as far as I possibly can and then let it go, it's going to oscillate big amplitude, right? But it's going to, the period is going to be exactly the same amount of time as if I just pulled it down a little bit and let it go. And so the amplitude does not impact the time. The time is independent of amplitude. It only matters the spring constant and the mass. All right. So here's this picture you've seen before, the oscillating mass on a spring. And I'm going to tell you that the mass is 3 kilograms and the spring constant is 4.9 newtons per meters. That would be a different kind of thing. 4.9 newtons per meter. I'm going to calculate the period of oscillation and the frequency for this system. Okay. So here I have time equals twice pi times the square root of the mass divided by the spring constant. Mass, spring constant. Plug them in. 3 divided by 4.9 is 0.6122, yada, yada, yada. Square root of that is 0.78246,079. And notice this is Newton meters. When you square root Newton meters, you get seconds, which is interesting, and you can look at the book for the derivation of that. So now I have seconds times 2 pi, and I get 4.916346 seconds. Correct for significant digits, 2, 2, 2, t equals 4.9 seconds. So there's one cycle in 4.9 seconds. It takes 4.9 seconds for one cycle to happen. Well, what's the frequency then? Frequency is just the inverse of the period, right? So 1 divided by t, 1 divided by 4.9 is 0.20340 hertz correct for significant digits again, and I have 0.20 hertz, so approximately 0.2 cycles per second. So that's calculating time for simple harmonic motion. Now, ideal pendulums. An ideal pendulum, just like an ideal string or an ideal pulley, doesn't actually exist. An ideal pendulum is a point mass, so all the mass is at one point, and it is suspended by an ideal string, so no friction, no mass in the string, of length L. And we use a little cursive L for this because it's different than just the length of the arm, which we will care about next week. Here we're looking at the distance from the center of mass of the pendulum bob to its point of attachment on the support. And that is the distance from the center of mass up. We don't care about the distance of the arm, we care about the distance to the center of mass. Okay? And the pendulum, it's much more complicated. And your book takes you through why it's more complicated. I'm just going to tell you it's more complicated than a simple oscillation. There's more to it than a mass on a string. Okay, than a mass on a spring, excuse me. For small degrees of displacement, if you just move the pendulum a little bit and then let it go, it's going to behave like simple harmonic motion. If you whack the pendulum, it is not going to behave like simple harmonic motion. And so for this class, we're going to be looking at motions or displacement of pendulums less than 1/8 of a rad, less than pi divided by 8, or approximately 22.5 degrees. Okay, when you get beyond this, then the equations stop working for pendulums, and you can worry about that in college. Okay, so for right now, pi divided by 8 is the biggest displacement we're going to get measured from the vertical, and I'll show you how we get to that. But the period of a pendulum, how long it takes to go from one point, oscillate over, and oscillate back, is a very similar equation. So let me just show you one more time the equation for a spring. T equals 2 pi times the square root of mk, m divided by k. Here I have t equals 2 pi times the square root of L divided by the absolute value of g. Now this is gravity. Why the absolute value? Well, because oftentimes people flip the orientation of the Cartesian systems here for pendulums, so that positive is down and negative is up. And so just to make sure that we can make this equation work depending on how you've oriented your system, we use the absolute value of g. Okay, but it's probably almost always going to be positive. That's given to you anyway, so don't worry about it. So L, the length of the ideal string going to the point mass divided by the value of gravity's acceleration. Now notice that nothing in here is a variable except L. Pi, as we know, is just a stand-in for a number. G is a stand-in for a number, right? We don't have to, what is pi, what is G? We just need to know what L is, which means that the only thing that controls the period of a pendulum is the length from its support to its center of mass. So here's some pictures for you. So this is just to illustrate how a pendulum is a little bit more complicated than a spring. Here we have the force, the restoring force that changes direction as the pendulum bobs back and forth, right? And the restoring force changed direction on a spring too. It pointed up, then it pointed down, then it pointed up, then it pointed down. But it isn't, in this case, it isn't just left and right. In fact, the restoring force kind of flips, and it actually, at this point, at the peak of displacement, is actually pointing up, which is weird. So it's a complicated thing, but as long as the pendulum isn't moving very far, then we can use these same kinds of equations. So a pendulum is a massive bob. This is where all the mass is on a massless rod or a massless string, and we look at L as the distance from its center of mass to its support, not the distance of the bar itself, but the distance to the center of mass is what we need. Okay, so let's do some math. Given a pendulum where the distance from the center of mass to the support is 1.25 meters, calculate the period of oscillation. Now we don't care how heavy this is. This could be 1 gram, it could be a car. But if the mass is suspended on an ideal string, 1.25 meters from the center of mass. It's going to be exactly the same. So 2 pi times the square root of L times divided by the absolute value of G. The absolute value of G, 9.81 meters per second squared. L is 1.25 meters. And so we do the division, we get this. We take the square root, we get this. We multiply by 2 pi, we get this. 2.2428507 seconds. Or correcting for significant digits, 2.24 seconds. All right. Now, this equation is kind of cumbersome, and it comes very close to having terms that cancel out. Let me show you some cool algebra. 2 pi times the square root of L divided by the gravitational constant G, okay, or the acceleration of gravity. Now, G is 9.81. I can break this square root apart, and I can say the square root of G is underneath this whole thing, and this is exactly the same statement, right? 2 pi times the square root of L divided by the square root of G. This is a synonym with this, alrighty? Now, G is 9.81. The square root of G is 3.132091. See how close that is to pi? Pi is 3.1415. Really close to pi. Not the same, but really close to pi. So depending on how many significant digits you have and how many significant digits you're going to be expected to express in your answer, you can approximate the square root of G as pi. Well, now you have 2 pi divided by pi. The pi's cancel out. So now you have just 2 times the square root of L. That's a lot easier to work with. 2 times the square root of L is a lot easier to use. You don't have to do as much work, okay? Now, it isn't exactly the same, but you'll only know that it's not exactly the same if you've got a lot of significant digits. So let's go back to that same problem, and I'll show you the difference in my modified equation and in the one that's in your book, okay? So given the pendulum where L equals 1.25, here I have 3 significant digits, okay? I'm going to approximate the period of oscillation here. So here's exactly what was on the other slide. Here's the answer we got for the other slide. 2 times the square root of L, 2 times the square root of 1.25, 2 times 1.118033, that is 2.236066. Now this number and this number are not the same, but I only have 3 significant digits, which means I'm supposed to round to here. 2.236 is 2.24. 2.2242 is 2.24. So it doesn't make a difference with only a couple of significant digits which of these equations you use, and this is heck a ton easier, okay? If you see that you're going to be expressing your answer in 4, 5, 6 significant digits, go the hard way. You'll get the right answer. If it's 1, 2, 3 significant digits, take the easy road and do a little bit less work, and you'll get there just as well. Okay? That is it. If you have any questions, post them in the comments field below, and I will address them tomorrow or tonight if I see them. Have a wonderful evening. God bless you. See you tomorrow.